So we saw how to verify that functions are inverses of each other, but now what about if we're just given a function and we're asked to come up with the inverse of that function? So let's start with f of x equals x plus 3. We already saw what the inverse of this should be. It should be x minus 3, but how do we get there without it being given to us? So one unique property of inverses, which you may have noticed just looking at these, it wouldn't have been very obvious yet though, is that the domain and the range are flipped. Okay. So this is going back all the way to what we looked at when we first started talking about inverses. We can see that the domain of f is the range of f inverse. Okay, the destination of f inverse, right? The domain of f inverse is the range of f, right? So the range and domain are flipped. In other words, if we just add on to this, f inverse, okay, the y values, and then the x values, right? So the domain and the range is flipped. We think of the domain and the range as the x and the y values. So that's exactly what we can do to find the inverse. We can swap the x and the y values. So what I mean by that is that we will take this. Remember, this is really y equals x plus 3. We just use the function notation. So for f inverse, the notation gets a little bit weird here. What we're going to do is we're going to flip these around. Okay, so we're going to get x equals y plus 3. And then we're going to solve for y, right? We still want to isolate y. So in this case, we'll subtract 3 from both sides. And we'll get x minus 3 equals y. So this is the inverse function. This is f inverse of x. Okay. So you can, it's kind of easier to switch back to the y notation here, but you can keep the f notation just as well. Like if you start with f of x equals x plus 3, maybe then you write, x equals f inverse plus 3, like that, right? And then you solve for f inverse. So that notation kind of makes a little more sense, but most people just like keeping the x and y variables in here instead of having to work with f in the function, like in the equation itself. We usually don't like use f algebraically, right? We usually just keep it on one side of the equation where we don't touch it. So it's just a little bit weird, but it's perfectly fine. It even makes more sense, in my opinion, to kind of do it like this. But we'll go back to the x and y notation when we're solving these here. Okay, so let's do some different functions that we haven't seen yet. Maybe if we do like the square root of x plus 1. Okay, we saw the square root of x should have a inverse. Here we're just moving it vertically up by 1, so that should still have an inverse, right? That's not going to affect whether it's 1 to 1 or not. So for f inverse, we flip the x and the y. Okay, and then we solve for y. So we get x minus 1 equals the square root of y, and then we square both sides. And we get y equals x minus 1 squared. We could just leave it like that. So this is f inverse of x. Okay, and of course it's good practice to verify that they are indeed inverses of each other at this point. But it's okay. You don't necessarily have to do it every time. It's just a way to make sure that your steps were correct. Back to that special case, 1 over x, we already saw it's its own inverse. How does that come up algebraically here? Okay, so f inverse, we have x equals 1 over y. So we multiply both sides by y. We get xy equals 1, and then we divide both sides by x. Okay, so we get y equals 1 over x, which is f inverse. So again, we verify algebraically it's its own inverse. Okay, showing an example now of the domain restriction that we talked about. If we have f of x equals x squared, where x is greater than or equal to 0, now we can define the inverse, right? Because this function is just this, right? It's only the right half, the positive half of that function, so we're good on the horizontal line test. So how does this come up algebraically then? Okay, so we have x equals y squared. So we take the square root of both sides, and because x is greater than or equal to 0, we don't need to consider the negative square root. We only need to consider the positive square root. So we simply get that y equals the square root of x. Okay. So I bring this up because on this one right here, you might have realized if you think about this, this is x squared. This was, first of all, this was the inverse function of the square root of x plus 1, right? This is x squared moved to the right 1. Okay, if we think about the graph here, so it's going to look something like this. But this can't be the inverse, because if we think about it, the inverse of the inverse has to be the original function, right? If we invert this again, we should get back to the original function. But we can't find the inverse of this, so it doesn't make any sense. So to do this properly, we really needed to restrict the it's not that we did it improperly, it's that, okay, we need to think about the range of this function. Okay. The range of this function, I'll put it in green here, right? This function is a square root function moved up 1. Okay. So it looks something like this. The range of this function is 1 to infinity. So the range of f is the domain of f inverse. Okay. So the domain of this function is 1 to infinity. So we didn't do anything improper, but we need to specify that because the inverse doesn't exist on the entire domain. It only exists on this limited domain. So if the domain or the range is anything other than all real numbers, we're going to need to specify this with the inverse, because the inverse is only because the domain and ranges are flipping. If the range is limited on 1, it means the domain is limited on the inverse, right, or vice versa. So we really need to specify these as we go if it's anything other than all real numbers. Okay. On this one, it doesn't actually matter. On 1 over x, the domain and range is everything except for 0. So when they flip, they're both just everything except for 0. So the domain is the same in this case. So if the domain and range are the same, it's not going to make so much of a difference. On the straight lines, it's all real numbers, right? So there it didn't matter. So yeah. Okay, so let's do one more example here. Here's a nice one. Give us a little application problem. This is the formula for converting from Fahrenheit to Celsius. Okay. So you subtract 32 from the Fahrenheit and multiply by 5/9. So let's find the inverse function. In other words, what's a function that will let us convert from Celsius to Fahrenheit? Okay, so the inverse function, we flip them around. Sorry, in this case, we don't even need to flip them around. All we need to do is just solve for f. So this is kind of a unique case, right? We just multiply by 9/5 equals f minus 32. And then we add 32 on both sides. Okay, so we get f equals 9/5 c plus 32. Okay, so in this case, we just needed to solve for the opposite variable. Okay. All right, maybe one more here. Let's say f of x. Sorry. Let me make that a little bolder. F of x equals 2 over x minus 3 plus 4. Okay. So for f inverse, we flip the x and the y around. So we get x equals 2 over y minus 3 plus 4. And then we solve for y. A few steps we have to do here. Subtract 4 from both sides. X minus 4 equals 2 over y minus 3. Now this can look a little bit tricky here. Move over here. In general, if you have the variable you want isolated in the denominator, you got to multiply on both sides by it. So we'll do y minus 3, x minus 4 equals 2. Multiply both sides by y minus 3. Now we don't want to multiply this out because it's going to make it more complicated. Instead, we're going to bring the x term over. Okay, divide both sides by x minus 4. So we have y minus 3 equals 2 over x minus 4. And then we simply add 3 to both sides. Okay. So this is the inverse. Okay. A couple quick things I want to put on the end of this video because they're just kind of quick things, don't really need their own video. You can do this same thing with a table. I really like problems like this where you're given a table of values like 0, 1, 2, 3, and I don't know, 3, 1, 2, 0, something like this. And then you could be asked like, okay, f inverse of 3, what is that? Right? So f inverse of 3 implies that f of x equals 3, right? Because the x and the y's are flipped. So you're looking for the f value when, or the x value when f is equal to 3. So in this case, you're going to get 0. Okay. So you really want to think about the relationship between f and f inverse here. If we're doing f of, I don't know, f inverse of 1, in this case we'll get 1, right? Because we're thinking where is f of x equal to 1? Okay, which is when x is equal to 1. So I like these kind of problems because they just really make you think about the relationship between a function and its inverse function. So these are good things to practice. One more thing about the graphs of the inverse function. And I didn't spend a lot of time on this because it's more like a neat thing, not something that we use a lot practically. But again, because the inverse function flips the x and the y values, the way you find the graph of an inverse function is by reflecting over the line y equals x. Okay, so this line y equals x, this is like a 45-degree angle at the origin, right? It's a straight line with slope 1, y-intercept 0. So if we take maybe x squared, right? X squared, where x is greater than or equal to 0, we know that its inverse is the square root of x, right? Square root of x. When we graph that, it's going to look like this. Okay, so we can see it's a reflection over y equals x. So just kind of a neat thing. If you take the graph of x cubed and you reflect it over y equals x, you would get the cube root graph. Okay, so let's go over there just to look at these parent graphs again so you can kind of see that relationship. You can see this cube root graph right here. It's just kind of the reflected version of this x cubed graph, specifically reflected over the line y equals x. The rational function. Again, if you reflect this over the line y equals x, it's going to stay exactly the same because it's its own inverse, right? So that's just kind of a neat property here. So that's just a quick way for you to be able to kind of visualize what the graph would be like. And you can also see, like, if you did it with things that don't have inverses, like if you did it with the absolute value of x, if you reflect over the line y equals x, you would have something like this, right? And that's not a function, right? So that's another way we can tell it's not invertible. When we reflect it, it doesn't pass the vertical line test, so it's not a function. Okay, so it all goes back to the fact that the domain and the range are the opposite for the inverse function, right? The domain of f is the range of f inverse. The domain of f inverse is the range of f.